screen so that we can talk about the more about the definite integral. And in particular, what we want to talk about is what do you do, like we don't know how to calculate these things exactly yet. Okay, now it'll turn out that there's a method for doing that. Last time, we were able to calculate things exactly for a couple of reasons, right? We were able to, like if the function was built out of straight lines, right, then we could just use the fact that we understand the area of triangles and rectangles and stuff like that, right? That wasn't hard. If the curve described a circle or some part of a circle, we could probably get it from geometry. And if there was some sort of symmetry of the curve that we could exploit, like the sine one, I think we did that, where it was pretty clear that the top half of, or the stuff above and the stuff below were exactly equal, even though we didn't know numerically what each of those was. We could pretty clearly argue that the sum was 0, and that was it, okay? So the question is, what do you do, though, if you've got a curve where we don't sort of know the answer exactly, and it's curvy in such a way that, like, there's no way to just throw geometry at it, right? So we've hit the limit, if you will, pun intended, of what geometry can do for us, okay? Okay, so let's take this curve here, 1 over x, and what we're going to try and estimate is the integral from 1 to 5 of this thing. All right, so let me just graph that here in GeoGebra. All right, options, labeling, new points only. Okay, so there's my curve, 1 over x, and then I'm going to kind of zoom in on it a little bit and frame in this part of it, because that's all I care about for now. So we're interested in this curve from 1 to 5, okay? So I've got this function, 1 over x, just a hyperbola, no big deal. So if I want to describe the area, it'd be sort of, I'm going to shade, if you will, with my mouse cursor up to there, okay? Could we estimate that? How could we estimate that? What would be, one technique? Can I just kind of count up all the little boxes that are underneath of it? And if I know the area of each box, then good. Okay, yeah, so we could estimate it by just kind of being doing some counting. But I could also do it by saying, all right, let me come up with a bunch of points here. This point, this point, this point. Oops. Actually, you know what? Let me do it this way. Okay, so I've just dropped 5 points here on the curve, A, B, C, D, E, okay? And I've picked them in such a way that, picking integers here is kind of convenient. I didn't have to, but picking these 5 will kind of make it easy from a picture drawing standpoint. And the idea is that I could do this for 500 just as easily as I could do for 5, with the exception of that I have a lot more stuff to draw, right? But the idea is the same. Okay, so what I'm going to do is this point A defines for me a rectangle. Now, horizontally, I've spaced all these guys out by 1 unit, okay? So I'm going to make the base of all of my rectangles 1 unit. The height of each rectangle I'm going to make depend on whatever the height of the function is at one of these points, okay? So for example, let me put in some more points. Just humor me for a second. Actually, you know what? I'm going to be smart and let the computer compute these. G equals 3f of 2. H equals 4f of 3. And I equals 5f of 4. Okay, so there, right? So I'll zoom in a little bit more because it gets a little hard to see them over towards the right because they get close. Okay, so what I could do then is I'm going to also drop a point at 1, 1, and where did that go? Oh, sorry, not 1, 1. I meant 0, 1. Or sorry, no, I meant 1, 0. Blah. Okay, there, and I'll have another point at 2, 0, and 3, 0, and 4, 0, and 5, 0, and that's enough. Okay, so what I've got here is if I'm going to use my polygon tool, and I'm going to define the polygon that is made up by, and let me zoom, sort of scroll this a little bit so it's maybe a little higher on the screen for you guys. Okay, so the shading, it's not so clear on the projector. It's a little clearer on my computer screen. But this polygon, right, is a rectangle whose left-hand edge I've made to correspond with the height of the curve. Its right-hand edge is, of course, that same height because it's a rectangle. And then the width of the thing was what I chose in advance, in this case just 1 as my constant width. I could have done this for any smaller or, for that matter, bigger width, but it would have just been a matter of zooming so that I could get this right. Okay, good? All right, so can we compute the area of that rectangle? And in this case, it just so happens that it's a square, but that's coincidence. Right? What is the area of that thing? 1 unit. Okay? Now, could I do the same game using points B, C, and D? Yeah, totally. Okay? So let me just draw those in for sake of, oops. There. There. And finally, there. Okay, now, what are the... oh yeah, thank you. It's not a rectangle. Yeah. There we go, that's better. Okay, so there we go, right? 4 rectangles. Now, they all have width 1, so that's nice. What about their heights? Well, the heights clearly are different. So what's the height of the second rectangle? It's a half, right, because that is the value of the function at this left-hand edge point. And then what's this one? 1/3, and then this one is 1/4. Okay. So what would be an approximation of the area under the green curve? It'd be the area of the 4 boxes. 1 plus 1/2 plus 1/3 plus 1/4. Okay. What is 1 plus 1/2 plus 1/3 plus 1/4? Yeah. Did you just do that in your head? Yep. Oh, nice. Okay. So 2 point something, right? Let's just double check that Owen. Let's be amazed at Owen's calculating prowess. Oh. Yeah. Thanks, bro. 2.0, nice. Okay. All right, so what's the exact answer? Well, I know this. It happens to be log of 5, okay, which is like, it's on the sheet there, 1.609, blah, 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 blah. So are we pretty close? Sort of. It's not great. You know, it's kind of like, have you guys seen the HBO Chernobyl thing? 3.6 Rontgen, not great, not terrible. No? Okay, never mind. If you watch the HBO series, you'll find that hilarious. I mean, as much as one can find anything hilarious in a series about a nuclear reactor blowing up. So, yeah, all right. So our estimate here, basically just slightly bigger than 2, is too big, right? In the sort of Goldilocks, like this porridge was too hot. This porridge was too cold. All right, we're too big. Okay, c'est la vie. Now, is it obvious from the picture why it's too big? Yeah, it's because my rectangles sort of go above the curve, right? So this first rectangle, for example, all of this stuff is not under the curve, but it is in the rectangle. So if I count it, I'm counting a little bit too much. And same for all the other ones, it's just they're not quite as bad, okay? So is it clear that this thing is definitely going to be an overestimate of whatever the true value of the integral is? Yeah? Okay, now, on the flip side, what's another way that I could have drawn all these rectangles? Well, notice that I made the left-hand edge of them all touch the curve. Could I have made the right-hand edge instead do that? Sure, okay. Let me draw one more point here at 1 f of 2, okay? And sorry, parentheses city here. 2f of 3, 3f of 4, and 4f of 5. Okay, so I could have done this on the other edge, okay? So let me pick my polygon tool again, and I'm going to draw now here a different set of them, and I'll hide the previous set once I'm finished here, just so it's a little bit more clear graphically. Okay, so what I'm going to do is I'm going to turn off the first 4 quadrilaterals. Okay, so now I've got this set, right? They all have base 1 again, right? That was just my choice. And their heights, this time, it's defined at whatever the right-hand edge intersects the curve, at B, C, D, and over there at E, okay? Now, from the picture, is it clear that this is an underestimate? Okay. What is the value of this estimate? Well, what's the area of each of these guys? What's this one? 1/2, 1/3, 1/4, and 1/5. Add all those up, or have our wizard at the back do it. 1.28. Okay. Can you say that with a little more enthusiasm? 1.28. Thank you. Man, great, Mr. Amore. 1.28. It's amazing. Right. Okay, yeah, 1.28, great. So, wonderful. Underestimate, overestimate. How could we have made our approximations more accurate? Smaller rectangles, okay, which means more of them, right? So if you have more rectangles, then the width of each one has to be a little smaller, okay? There's sort of the give and take relationship there. But even if I did this with 1,000,000 rectangles, wouldn't this still be an underestimate? It'd be a very, very, very slight underestimate. And then on the other side, if I had done the other kind of rectangles, it would have been a very, very slight overestimate. And the more and more of these rectangles we do, we kind of start to squeeze in, if you will, on the true value. Okay, so does that sort of make sense? Right? Now, in this case, for this particular function, we know what the exact value is using a different technique, which we'll talk about later, that it's precisely the natural log of 5, okay, or which numerically is like 1.6, blah, 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 blah. Okay, so if we did this, like I said, with a billion rectangles, we would probably get 1.6094, and then maybe we'd be off in that next digit slightly or something, right? Point being, we're going to be really dang close, but we're never going to be perfect unless we use infinitely many rectangles, and that's, you can't just do that, sort of, right? We will, but one does not simply, yeah. Okay, so does that kind of make sense? Now, how is it that I knew, okay, so other than just not being a moron and looking at this and saying, well, clearly those rectangles are underneath the curve, right, or above the curve, what was the property of the curve itself that told me that I was going to have an under or over estimate, depending on which rectangles I used? Okay, so this is purely about the curve, right? I could have known this before I did any drawing, that the left-hand method would have been an overestimate, and the right-handed version would have been an underestimate. Why is that? What's true about this curve? I'm sorry? Oh, sorry. Maybe this is a convention thing. The rectangles that I've drawn here are the right-handed versions. Okay, now why do I say that they're the right-handed versions as opposed to the left? Because which edge of the rectangle's height is right on the function? The right-hand edge. So this one's right-hand edge is there, this one's right-hand edge is there, and so on. The other version, the first set that I drew, were the left-handed versions. Okay. No, go ahead. What's? Huh? You good? Yeah. Okay. So right. Left. No, right. Right. It's like in. Okay. Here's a movie reference. Surely you guys. Have you all seen The Incredibles? Yeah. Okay. So the scene right after they've got the flying camper going on, and then they land and they're on the freeway, and then that'll take us to the financial district. Don't take 7th, and then they're arguing. Right. Yeah, I loved that scene. And they're like, that's so cool. We want to go downtown. How many of you guys have had that experience being in the car with one of your family members? Yeah, right. Yes, actually, this one's a funny family story. So, so my father was in the Marine Corps for 15 years basically, and so they had me when they were stationed in Guam, which is an island in the South Pacific, a very long way away from here, basically on the other side of the planet. Okay. And then we moved to Virginia, then we moved to North Carolina, and we were there for 3 or 4 years, and then that's when he left active duty, and we moved to Texas to sort of begin civilian life. Okay, yeehaw. Anyway, so my dad had to stay back, and he was going to supervise the movers coming to pack up the house, and my mom, my sister, who was like 2 or so, and I were going to drive all the way to Texas over the course of several days, right? And so we're in North Carolina. The town we were in was not right on the beach, but pretty close to it. And so our first sort of leg is to get to Charleston, South Carolina, where we then meet up with I-20 or whatever it is to go basically west across the country. And, or I-30, I guess. So we get into Charleston, and I think, you know, we stop, we have some food, right? We get gas. And my mother has a horrendous sense of directions. So we're driving, and we come up over this hill, and we get to the top of the hill, and there, spread before us, is the full glory of the Atlantic Ocean. I mean, it was a beautiful scene. But it's like, Mom, so I'm like 7, right? Mom, this is the ocean. That means we are facing east. Texas is west. I think you've taken a wrong turn. She's like, yes, I know, thank you, God. So thank you. And we eventually made it to Texas. But this was, as you can imagine, in the days before cell phones and GPS. Only the military had GPS, and it was still kind of new at the time. And yeah, you had to navigate with atlases. Yeah. Anyway, so yes, my mother also has a very bad sense of direction. Okay, anyway, so left, right, no left, right. Okay. So what was it about the green curve, though? What calculus property does it have? Huh? That's an algebraic thing. Yeah, so it happens, actually the second derivative of this one's positive, right? The first derivative, however, is negative, and that's the one that we care about here, right? I know that the left-hand method is going to be an overestimate because the curve is decreasing, right? If the curve were increasing, it'd be the other way. And if the curve were a straight line, well, that's kind of neither increasing nor decreasing. Then, well, if the curve was a straight line, we wouldn't have to do any of this stuff, right? It'd be obvious. Okay, so we can understand in advance whether or not we're going to be over or underestimating based on the properties of the curve that we're dealing with and the method that we're using. Okay, so does this kind of make sense, right? It's a lot of drawing, a lot of calculation, but what really were we doing? We were really adding up the area of a bunch of rectangles, okay? They all had, in our case, a constant width. The width doesn't have to be constant, but could you see that that would make this a little easier if the width was always the same number? Yeah, I mean, could I have made this rectangle, like, made this one 0.2 wide and then this next one 0.4 wide? I mean, I could have done that, okay? But isn't it a little bit more expedient to do it this way? Yeah, okay. Now, the nice thing about that is, well, we'll talk about that later. Okay, so what happens if I use more and more rectangles? To the true value, okay, whatever that true value is. Now, we may or may not know what that true value is in advance, okay, because there's rules that we haven't talked about yet, okay. Okay, so here's a good question. Let me put all 4 of the other ones back in. Okay, so what did we get for our left-handed method? It was the, what did you say, 2.083 repeating? Okay, so let's just say 2.08. What do we get for the other one? Okay, what's the average of those two numbers? Which is pretty dang close to the true value. Okay, so that method of averaging the two is called the trapezoid rule. Okay, so we've done the left and right-hand rules because we did left and right-handed versions of the rectangles. Okay, the trapezoid rule would be just the average of them. Okay, now, based on the graph, why do you think we call it the trapezoid rule? Yeah, Ian. Yeah, instead of drawing, so like my rectangles, I've got, like, let's take this first rectangle, the segment AF or the segment OB, right? But could I have done instead a trapezoid whose base was JK and whose top edge was, rather than being AF or OB, so it's a rectangle, I instead do AB. Yeah? Okay, so let me just draw that one in for the sake of demonstration. And in this case, I've already have all the points I need, so I don't need to draw any more. Okay, and then let me hide all the other ones just for the sake of clutter. Okay, so there would be the first trapezoid, and then I could do the same game for the other three, right? Okay, does this look more accurate than the rectangle methods? Yeah, okay. And because we kind of are hugging a little closer to the curve, and hence we're not overshooting by as much. Okay, so this looks like it's a slightly better method. However, there's more arithmetic to do, right? So this is another sort of a trade-off that you guys have to think about, is how accurate do you want the answer, right? The more accurate you want it, the more work you got to do. Okay, so you basically have to think about where are you on the continuum of perfection and absolute laziness, right? So there's a scale between being as lazy as possible and being as perfect as possible. Where do you want to be on that scale? Well, it seems like a reasonable place, right? But that actually is going to, I think, depend on context and what you're trying to do with this, right? If we're in a calculus class and we're off by like 0.1, is anybody going to die? No. If I'm like trying to design some new medical apparatus or a rocket to go to Mars, right, I better be right on the money or else things blow up. Okay, so, right. Now, for this curve, why is it, well, first off, does this trapezoid method here over or underestimate? It overestimates, okay? That's pretty clear from the picture, right? What property of the green curve tells me that this one would be an overestimate? We already know that the function is going down. It's decreasing, meaning that its derivative is negative, right? But what else is true here? The concavity of it, meaning its second derivative. So this is where the second derivative comes in, okay? So this function is concave up. We haven't really talked a whole lot about concavity yet. We'll come back to that. But it's curved in a particular direction, right? So it's sort of what's happening to the slopes of the tangents as I move further to the right. The slopes are all negative, okay? But as I move to the right, what's true about the numeric values of those slopes? Like at point A, what's the slope of the tangent line roughly? Ish, okay? That's actually exactly what it is, but great. What about at point B? Is it bigger than -1 or less than -1? Well, okay, technically it's bigger because they're negatives, right? Okay, so yeah, good. Sorry, that was a poorly worded question. So if the slope at point A is -1, the slope at point B, would you expect it to be like -0.5 or -2? Roughly. 0.5, right, which is bigger than -1. I mean, yeah, I can see why you might say that's smaller, but the number line is only ordered in one direction, right? So, yeah. Okay, does that make sense? So that's the sense in which we say this thing is concave up because the slopes are increasing values. We'll talk a lot more about that in probably a week or two. Probably more like 2 weeks. Okay, so this is sort of the idea here of what we're doing with the left and the right-handed method. Those are called Riemann sums, okay? And the trapezoid method is sort of a, not too difficult extension of it to be slightly more accurate, okay? Okay, so look at the sheet at the very, very tip top of the second page, okay? This is what formally defines the definite integral, okay? So the rectangle methods, either left or right, it doesn't really matter which one we pick, okay, so just pick one. What if we said would happen if you used a bajillion rectangles? Okay, so if you use 10 rectangles, it's going to be not great, not terrible. If you use 100, it's going to be much better. If you use a bajillion, it's going to be like almost right spot on the money. Okay? So what's the moral of the story here? More rectangles means better accuracy. All right? So what about if I want to use infinitely many rectangles? Now, I can't just do that, right? I can't sit here and try and count up infinitely many rectangles. But what I can do is say, all right, let's suppose I use n rectangles. And then I take a limit as n goes to infinity. Now what are we doing? The second I throw a limit in front, where are we? We're back in calculus territory. Okay, so how we do that limit and the details of it is what we'll talk about next time, or start talking about next time. Okay, so does that kind of make sense? The big idea here? Yeah? Okay, so let's go to, on page 2, oh, sorry, there's one other method we could do. Look at the graph on page 2 at the very bottom. Well, okay, sorry, let me back up. Page 2, part B, right? I've drawn one of the trapezoids. Draw all of them, okay, if you haven't already. Okay, and while you guys are doing that, I'm going to plop a bunch more points up on my graph just to make it even more spicy. Like we're getting to mango hob territory. I saw they have a couple of new flavors. I haven't actually been out there in a while, but.
I tried it.
Which one was it? The truffle one? How was it?
It was pretty good. It was like a sweeter buffalo sauce.
Yeah, it's kind of an interesting combination to do truffle and buffalo sauce, but because truffle can be a little overpowering if you don't use it right. And there was another one, though. Do you remember what it was? No? Okay. All right, so let me hide my trapezoid. So are we cool with the trapezoids? Oh, and I should mention, just by the way, how did we compute the trapezoid value? What did we say that we could just do? We could average the left and the right-hand methods. Okay. Well, the downside to that way of saying it is that means that you have to already know the left and the right-hand methods. What about if you didn't? What about if you wanted to go directly to the trapezoid rule? Well, what's the formula for the area of a trapezoid? You guys happen to remember? Nope. It's the base times the average of the heights. Okay? So my point, though, is that could we have computed the area of that trapezoid without having to do the left and the right-hand methods first? Yeah. Okay, using what I just said, that if we have a trapezoid like this, right, the area of it is the base times the average of the two height values. Okay? Now, if you happen to already have the left and the right-hand answer, then just average them and then you're done, right? But if you don't already have those, then this is a different way of doing it. Okay? All right, does that kind of make sense? Yeah? Okay. Some of this stuff, like honestly, you guys will get more comfortable just by doing a bunch of computations. And this is the, well, okay, there's a couple of points on this from an assessment standpoint, right, so what I would want you guys to do is, like the 2.08 or whatever, the number, I don't care, right? What I care is how you built that, right? So you built it by saying, oh, it's f of this times 1 plus f of that times 1, right? So I'd rather you show me sort of the formula that you would then punch into the calculator and draw the picture and that sort of thing. Does that kind of make sense? Yeah? Okay. All right, so I've put in here, so now, well, first off, let me pause. Any questions on the trapezoid part before we move on to the next sort of method? Gucci? No? Okay. The other way that I could have split the difference was, instead of using the average of the left and the right, I could have used the middles, right? I could say, well, point A, the rectangle that goes with that is going to be too big, and point B is going to be too small. So what about if I pick the height of it not based on the left or the right, but based on the middle of the width? Could I do that instead? Sure. Okay. So let me draw that picture. All right. So, oh, I need a few more points here to do that. So I need 1 comma f of 1.5, and I need 2 comma f of 1.5. Okay. And I'm starting to run out of letters. Okay, so there. All right, still a rectangle as opposed to a trapezoid. Okay, so in that sense, this is a little simpler. But a sense in which it's not as simple is the height of the rectangle is defined by the point S. Okay, where is S? What are its coordinates? Yeah, well, that's its y-coordinate, right? So how do we get 1.5? Well, what are the x-coordinates of A and F, or equivalently J and K? Right. So I just found the midpoint of the x distance there. Okay, and in this case it's 1.5. Okay. All right. Does that part make sense? So it's halfway between both edges of the rectangle. And then I plug in 1.5 to my function, and I get whatever I get, and that's the height that's going to be associated with this. Okay, so this defines a new rectangle, the one that I've sort of sketched in there, and does that rectangle over or underestimate? Well, that's not as easy of a question to answer this time now, is it? Because, why? This little, like, in a sense, it both over and underestimates. Okay, now it can't really do that, but it's missing this chunk, but it's overshooting on that chunk. Okay? Which chunk do you think is slightly bigger than the other? The missing chunk or the overshot chunk? In this case, the missing chunk is slightly bigger. Why? Because the function is? Yeah, it's decreasing but concave up. Okay, so at the left-hand edge of that, right, at point A, what's the value of the slope, roughly? Yeah, -1. At the point S, so my finger is going to, actually, you know what? I can do something really cool with this. I'm going to plop a point, and this is a movable point, so I can drag it, and it stays on the curve. Okay, and then I'm going to use my tangent tool, and I'm going to say I want the tangent at this point to this curve, and bam, right? There's a tangent line. Okay, good? So as I drag this point, what's true about the slopes? They're getting less steep, so the slopes are increasing. Now, they're all negative, right? Because the line's going down. So here, the slope's one thing. here the slope it's gentling out, and now it's even more gentle and more gentle and more gentle and so on. Okay, does that make sense? Have you guys ever seen this program before? No? Okay, I love it. It's called GeoGebra. This is the version 5 classic, which I like better in many respects than GeoGebra 6. They changed a lot about the interface, and I like the old interface better personally. But I use this a lot for research, actually, because can you guys imagine that this would have been a godsend when you were in geometry in high school? Yeah. It also, I mean, how do you think I make, like, really nice geometry diagrams? This, right? Anyway, okay. So in this case, the midpoint rule, we've said, is a slight underestimate. Yes? Because the little part there between A, W, and S is a little bigger than the part between S, Z, and B. Okay, those two little slivers. Okay, good. Now, it's going to be, sorry. As you can tell, I have a meeting with Dr. Olafson in 15 minutes. It's going to be, well, okay. Do you think this midpoint rule is going to be better than the left or the right-hand rules? Yeah, probably. Reasonable guess. Okay, now the real tough question is, how does it compare to the trapezoid rule? That is definitely not nearly as obvious. Okay, so the first thing is, let's actually just calculate what would the estimate be for all 4 of these rectangles if we had done these midpoints instead. Okay, make sense? All right, so do that real quick. Well, let's take the second rectangle just for sake of demonstration. What is the x-coordinate of point T? 2.5, right? And how do I know that? It's because it's halfway between 2 and 3, okay? And then, so I'm going to plug 2.5 into my function, which is what in this case? 1 over x, and then I get whatever I get. Now, in this case, because it's 1 over x, we could be smart. 2.5 is really what? 5 divided by 2, and so f of that is 2 divided by 5, right? Which is 0.2. 0.4. By 0.2, I meant 0.4, right? Okay, so compute the total of all 4 of those guys, and what we want to do is sort of compare this to the other answers that we've gotten. Okay? Does that make sense? All right, this part of it kind of sucks because it's number crunching, but c'est la vie. And while you guys are doing that, I'm going to draw in the other midpoints so that we can do some checking. Let's see. All right, so I need to put a point at 2, f of 2.5, and 3, f of 2.5. I need to do 3, f of 3.5, 4, f of 3.5, 4, and 4, f of 4.5, and 5, f of 4.5. Okay. Now my figure is starting to get a little bit cluttered here, but you guys will forgive me. Oops. Oops. All right, so what'd you guys get for the estimate here? 1.58, does that sound about right? Okay, which is pretty good, right? What was the true answer that we were supposed to get, like the exact answer? Okay, so what did you get for the midpoint rule? You got 1.58-ish. What did we get for the trapezoid rule? It was 1.60, and then there'd be some more digits, right? Okay, what did we say about the trapezoid rule? Was it going to be an overestimate or an underestimate? Trapezoid. Trapezoid was an overestimate. Midpoint is in this case, right? That is all because of the function that we're dealing with and the properties of that function. So don't think that the trapezoid rule always underestimates. Okay, it depends on the function. This example, it underestimated. Okay, now, here's, I guess, maybe a slightly harder question just because of how many decimal digits you kept up with. Well, actually, no, it's okay. So we have 5 values that we've computed, correct? The left-hand one, the right-hand one, the midpoint one, and the trapezoid one. Okay, those 4 we drew in and we computed and we sketched stuff. Okay, what's the 5th value? The exact value that I've told you in advance. That was the log 5 thing. Okay, so what's the order? We've got 5 numbers, right? None of them are equal to any of the other ones. So what order do they go in? Who's the smallest number? Right-hand method. Okay, who's bigger than that? Who's next? Midpoint, followed by the trapezoid, followed by the exact, or no, not the exact. Trapezoid's bigger than the exact, remember? So let me sketch this up on the board then. Okay, so for this particular curve, who was the smallest value? Right hand. Who was bigger than that? Midpoint. The exact value was, in this case, right in the middle. Who was slightly bigger than that? Okay. So in this case, the order of the estimates is right hand, less than the midpoint, less than the exact value, less than the trapezoid, less than the left hand. Okay, does that kind of make sense? All right, so kind of an interesting question, we'll have to quit here, is which one's better, midpoint or trapezoid in this case? Who's closer to the true answer? In this case, the trapezoid, okay? But yes, okay? All right, so I think we're pretty good there. So what I'd like you guys to do, just kind of as a, or actually, you know what, I'll have Champ save this as an SI thing, is the one in the very back, which is to basically do the same stuff, but for a different function. Okay, good? All right, have a fantastic weekend, guys. I also apologize profusely. I'm not done grading your things, but I promise, come hell or high water, you will have them on Monday. Also, I'm going to put up a link. I want every last one of you to schedule a retake with me sometime next week. Okay, so I'll put up like a booking thingamajig to do that. Okay? All right, have a great weekend. See y'all later.